Deep in the universe, far beyond our sight, some of the rarest and most valuable materials in existence are forged in one of the most violent events nature can produce: the collision of two neutron stars. To understand why this cosmic process is so extraordinary, we need to look first at what neutron stars actually are. When a massive star reaches the end of its life, it explodes in a supernova, blasting its outer layers into space. What remains is the collapsed Coron object so dense that a teaspoon of its material would weigh billions of tons on Earth. This remnant, called a neutron star, is only about 20 kilometers in diameter, yet has more mass than our entire Sun. These stars are extreme in every sense. They spin rapidly, some hundreds of times per second, and they have magnetic fields a trillion times stronger than Earth's. But the most spectacular event occurs when two of these stellar remnants, locked in orbit around each other for millions of years, spiral inward and finally crash together. The energy released in that moment outshines entire galaxies, creating not only gravitational waves, but also heavy elements like gold and platinum in quantities beyond imagination. For a long time, scientists speculated about where the universe's heaviest elements came from. We knew lighter elements, like hydrogen and helium, were formed in the Big Bang, and elements up to iron were created in the cores of stars through fusion. But gold, platinum, uranium, and other heavy elements required a different explanation, because forming them demands extreme environments where atomic nuclei can rapidly capture neutrons in what is called the R process, or rapid neutron capture. For decades, it was believed that supernova explosions might be the source. Yet, models didn't match the observed abundance of these elements across the universe. It wasn't until 2017 that astronomers got their long-awaited proof. That year, scientists detected gravitational waves from a neutron star collision, an event officially named GW1 70817. Alongside the ripples in spacetime, telescopes observed light from the explosion called a kilonova. Analysis of the light spectrum revealed the signature of freshly created heavy elements. In other words, we finally confirmed that gold and platinum, two of Earth's most precious resources, were born in these colossal cosmic smash-ups. The sheer scale of production in such an event is staggering. It is estimated that one neutron star collision can create more than 100 times the mass of Earth in gold alone. Imagine entire worlds made of nothing but gold and platinum suddenly cast into space. On Earth, gold is so rare that all the gold ever mined would fit into a cube measuring about 22 meters on each side. Platinum is even rarer, primarily mined in just a handful of countries like South Africa and Russia. And yet, in one single kilonova, nature manufactures more of these elements than humanity could ever dream of extracting over millennia. When we wear a gold ring or admire platinum jewelry, it's worth remembering that these metals were not simply mined from the ground. They were forged in a cataclysm that shook the fabric of spacetime itself. Each piece of gold on Earth carries a cosmic history billions of years old, born in the death throes of stars. The discovery has not only deepened our understanding of the universe, but also reshaped how we see our own planet. Earth's supply of heavy elements likely came from such collisions billions of years before our solar system formed. When clouds of gas and dust condensed to form the Sun and planets, they contained traces of these rare materials, sprinkled across space by neutron star mergers that had taken place in earlier generations of stars. Without those events, Earth would not have gold in its crust, platinum in its rocks, or uranium fueling its natural processes. In a sense, the sparkle of gold is a reminder of cosmic violence, a jewel created in fire far beyond human reach. But why do these collisions release so much material? When neutron stars collide, their dense matter is ripped apart and ejected at nearly 1/3 the speed of light. This matter is incredibly neutron-rich, exactly the right condition for our process nucleosynthesis. In the aftermath, radioactive decay of these freshly made elements powers the bright kilonova glow we can observe. That glow fades within weeks, but the elements remain, drifting into interstellar space, where they may one day seed new planets, life, and civilizations. What's extraordinary is that through gravitational wave observatories like LIGO and Virgo, we can now witness these collisions not just in light, but also in space-time vibrations, giving us two ways of observing the universe's most dramatic events. This field of multi-messenger astronomy has only just begun, but it promises to reveal more about how the rarest and richest parts of our universe come into being. The human fascination with gold and platinum has always been about rarity, beauty, and permanence. We mine them, trade them, and treasure them. But compared to the abundance in space, our earthly reserves are almost trivial. In fact, astronomers speculate that if humanity ever develops the technology to mine the debris of neutron star collisions or even gather metals from asteroids enriched by such events, we would access wealth on a scale unimaginable today. Of course, the distances are so vast that practical mining of kilonova remnants may never be possible. But the thought itself reminds us that Earth is not isolated. Our most precious resources are gifts from the cosmos. They remind us that we are part of a larger story, one written in the language of stars and explosions. The 2017 discovery also had another profound effect. It confirmed the theory of Einstein's general relativity in a new and powerful way. Gravitational waves were first detected in 2015 from black hole collisions, but neutron star mergers added a new layer of evidence. These waves ripple outward across the universe at the speed of light, and their detection has opened an entirely new window on the cosmos. With each detection, we may learn more about how often such events occur and, by extension, how much gold and platinum exist in our galaxy. Already, scientists believe that the Milky Way alone has experienced many neutron star mergers throughout its history, each one enriching the galaxy with heavy elements. Without them, Earth would be barren of these rare treasures, and human civilization would lack the tools, technology, and symbols of wealth that have shaped cultures for centuries. So, the next time you see gold glinting in jewelry or platinum shining in technology, remember the story it carries. These are not just commodities dug out of mines. They are relics of the most powerful collisions in the universe, pieces of cosmic history scattered across space and time, collected by gravity and delivered to our world long before humans ever existed. Gold and platinum are rare, not simply because Earth has little of them, but because they can only be made in the rarest of events, the violent union of neutron stars. They are as much the treasure of the universe as they are of Earth. Timeless reminders of how our world is shaped by forces far greater than ourselves. In the end, the wealth locked inside neutron star collisions is not about currency or jewels, it is about perspective. These metals connect us to the universe on a profound level, telling us that our planet's story is intertwined with cosmic catastrophes that happened billions of years ago. To hold gold is to hold a fragment of the universe's most violent past, a piece of a collision that lit up galaxies, a trace of matter born in unimaginable extremes. It is humbling, awe-inspiring, and a reminder that we are, in every sense, children of the stars.